I want to do a quick explanation of the logic behind this theorem, since it is a very useful theorem. So theorem 4.1.2 says that if you have a collection of vectors from a vector space, then the span of that collection is automatically a subspace of the vector space V. This is by virtue of the definition of span. So a span of vectors is the collection of all linear combinations. I'll jot that down. Oh no, my little writing tool's not working that great. Okay. Collection of all, let me just abbreviate, linear combinations of the vectors v1, v2 up to vp. So a collection of all linear combinations means if we have some scalar times c1, where c1 is just any number times v1, plus any scalar c2 times v2, okay, and so on, up to the last vector, in this case vp. So the span of these vectors, v1, v2, up to vp, is equal to, the collection of vectors that can be formed this way, where c1, c2, up to cp are just any numbers. Let's just put it that way, any real numbers. Okay, so think about the three conditions. If we have, this is certainly a subset of the vector space V, because since V is a vector space, it's closed under addition and scalar multiplication. So anytime we take a sum of scalar multiples of vectors within that vector space, it must be contained in V. So we're definitely looking at a subset of V. So if we can show that it meets those three conditions, then we know that it's a subspace. So first, that the zero vector is contained in this subset. I'm just going to write the span. Well, I feel a little bit uncomfortable with that. The span of these vectors. So the answer here, yes, it contains the zero vector, because we can just let all of the scalars, c1, c2, up to cp, if these scalars can be any number and it's contained in the span, then we could let them all be zero. And that would be contained in the span of these vectors. Is it closed under addition? Under addition. Well, the answer there would be yes. If we had take the sum of any two vectors in the span, then the result is going to be another vector in the span. I guess let's take as an example. So if W equals, let's say, C1 V1 plus C2 V2, if it's some element of the span, then it has this form. And let's let also the vector U equal, I'll use K for the scalars this time, K1 times V1 plus K2 times V2. So this other vector, if it's in the span, then it is some linear combination of V1 through Vp. And so when we take the sum of those two vectors, we could write that as, so if you take C1 V1 plus K1 V1, we could write that as C1 plus K1 times V1, which this is just some scalar times vector 1. And then we could do the same thing, let me switch colors here, with V2. We have C2 times V2, and then over here we have K2 times V2. So we could combine those to say C2 plus K2 times the vector V2. And again, we've got some scalar multiple of V2. And so you could do this for all of the vectors, V1 through Vp, on down to, you'll have Cp plus Kp times Vp. And so yes, it is closed under addition. You take any sum of any two linear combinations of these vectors, and you're going to have a new linear combination of the vectors v1 through vp. It's similar for scalar multiplication. If take this same vector, this generic vector w that's in the span, and suppose let's let s be some scalar. Suppose we do s times w. So that would just be s times each component here, c1 v1, plus s times c2 v2, plus s times c3 v3, okay, on down to s times cp vp. So if you multiply just any vector in the span by a scalar s, all that's going to do is multiply all your scalars times s, but then that's still a linear combination because it's still a combination of a scalar times a vector, scalar times a vector. So it's a linear combination of the vectors v1 through vp. Okay. So again, a span sort of by definition satisfies these three criteria. So it's always a subspace of the vector space V. So this is really useful. This gives you another way to prove that a collection of vectors is a span. If you lost my track of the pen. We had a previous example in the notes where we said consider the subset of two-dimensional vectors where the first component is 2 times the second component. So we could write this as y times the vector 2, 1. And so that subset W can be expressed as, well, let me write it this way, as the span of just the single vector 2, 1. And so from now on, thanks to this theorem, if you can express a subset as a span of vectors within a vector space, even if it's just a single vector, then by theorem 4.1.2, W is a subspace. This would be a subspace of R2, because we've got it's a span of just a single vector in R2.